Hey everyone, hope you're doing great. So today I wanted to talk about bad heuristics and how bad heuristics can lead to choosing a suboptimal path on a graph. So if you guys haven't checked out my first two videos on uniform cost search or A-star algorithm, I really suggest you check those out first. I have put the link of both of those videos in the description as well as on the top right section of this video. So in this particular example, I have taken it from the previous video directly, but I have changed up the heuristic values here. So the heuristic values, if you remember, they tell us how far away we are from the goal node. So this is some information which we are already given, and like in this particular case, B and D are sort of visually closer to goal node G. So usually they should have lower heuristic value than node SAC, but in this case, since I want to show like bad heuristics can cause a suboptimal path selection, I chose the heuristic cost of value 10 for node D, and for node B, H is equal to 1. So if you go according to all the steps of the A-star algorithm, what you will observe is that the path that this algorithm selects would be SPG for these heuristic costs, and that is a suboptimal path because the optimal path here is SADG, as we saw in the first two videos of this series. So that is the main issue with inadmissible heuristics. However, inadmissible heuristics will still allow us to go from the start node to the goal node G. So in that case, or in that particular sense, it is complete that you will be able to find a path from start node to goal node, but it might not be optimal as shown in this example. So the question that comes is that how do you ensure, or what is the criteria that needs to be satisfied so that you get an admissible heuristic? And in order to get that, you have to actually just satisfy this condition, which is that the heuristic value at the node n has to be less than equal to the optimal heuristic value, or the optimal cost to go from node n to G. So in this particular case, since this is an easy example, it's easy to figure out what are these H star n values. So for instance, if you're at goal node G, then H star n, it would be 0 because you're going from goal to goal. If you're at node D, then there is only one path that exists from D to G, so that cost is 2. So the cost to go, or the optimal cost to go, becomes 2. Similarly for B, it's easy to find out that H star B would be 5. If you are at node C, then again, it's sort of like similar to B and D. The optimal cost to go from C to G would be 3 plus 2 units, which is 5. If you're at node A, then you have two particular ways to go to G. One would be taking path A to C to D to G, and that cost is going to be about 7 units. One way would be to go from A to D to G, which is about 6 units. So since we are talking about optimal cost to go, then H star A would be 6 units. And similar procedure can be done for S, and H star S would be about 8 units. So if you see, the way I calculated this H star N value was that we went through each and every path and we picked up the minimum cost to go from node N to G. However, you can imagine that if this graph was really big, or it had a lot of nodes with a lot of connections, then it would be really difficult to find out what would this optimal cost to go be. So H star n would never be known a priori to you. If it's already known, then you know in a certain sense what the shortest path is, because in this particular case, H star s is 8. How did I calculate it? So it was calculated based on the fact that we already knew the shortest path was SADG, right? So that thing helps us in calculating this optimal cost to go value for the start node S. So now, instead of knowing the optimal cost to go, what we do is we try to build heuristic values which sort of are based on how nodes are kind of placed away from the goal node G. So in this particular example, what I wanted to show was that if your heuristic H value satisfies this criteria, then you would be able to get the optimal path from S to G. So for instance, in this particular case, HC, which is equal to 2, is less than equal to H star C, which is 5 here. And similarly for all other nodes, H of n is less than equal to H star of n. So again, if you apply the H star algorithm, what we see is that we get the path SADG as the final path from the algorithm, which is the optimal one. So this is a case where choosing an admissible heuristic that is like which satisfies this criteria, we are able to get the optimal path selection. Now, another thing that I do want to point out is that if your heuristic function is closer to H star values, then choosing or getting to the optimal path would be more quicker. That is like in fewer number of steps, you'll be able to find out the optimal path. So the left case is considering the H values that we had from slide 23 or the previous slide. And the right path or the right box is one where we considered H star values. And again, if you go through the H star algorithm steps, what you can see is that the the optimal path chosen by these H star values is way quicker to obtain than getting the optimal path in case where the H values are way different from H star. So the idea is that what we want is the H value to be as close as possible to H star, but obviously we don't know what H star is beforehand. And I just wanted to point out one slight thing regarding how you can find the H value. So for instance, in this particular case, suppose say you are given the position coordinates of start node, A node, C node, D node, B node, and G node on this XY graph. So you can imagine like this is a network of different cities and you are given these GPS coordinates. Now, can you find that heuristic H value? And for these particular node locations, you can use this Euclidean distance formula. And this Euclidean distance formula just tells you the distance between the node N till node G. So the H values that you see on this slide, they are computed using this formula. And moreover, you can also observe that the H values also satisfy the admissibility criteria. That is, the H value at node N is always less than equal to H star of N. So again, if you apply the H star algorithm, what you can observe is that you'll get the optimal path SADG after doing all the steps. So the thing that I want you to remember out of this video is that having an admissible H is critical for H star algorithm to give you an optimal path. And in case you don't have an admissible H, still you would be able to find a path from start node to goal node, but that could be suboptimal. So thanks for watching, and if you have any comments or suggestions, feel free to leave them below. Thank you.